All right, welcome to this video on Unit 2, Lesson 1 in Geometry. We are starting our unit on beginning geometric proof, which will have a lot of logic and proof in it. Our first lesson on is what are the types of reasoning, what is an axiomatic system, and a conjecture. So there are basically two types of reasoning that we use in mathematics. One of them is more mathematical than the other. We have inductive reasoning. I like to call that science reasoning. So I'm going to say science for that one. That's basically when you reason based on a pattern of previous events. They do that a lot when they do experiments. They're trying to confirm a conjecture or a conclusion by doing the same experiment over and over and over, having other people replicate it, because the more often you see the same pattern, the more you can make decisions based on that pattern. So it's based on a pattern of previous events. A simple example that you'll be familiar with is something like this. Okay, as if you look at that pattern, you can see that every single time 4 is being added to the previous number. So the pattern is adding 4 each time. And of course, the next term, sometimes you'll be asked to find the next term or the next terms in the sequence. We'll just find the next term, singular. We'll just find one of them, which would be 21. What's the kind of problems you'll have on your assignments? All right, the deductive reasoning is different. It's reasoning based on an axiomatic system. An axiomatic system is logical and it has assumptions and definitions used to prove rules. The system can build upon itself because rules can be now used to prove other rules. Okay, so we have to have reasoning based on a definition, an assumption that has been agreed upon, or a rule or property. We can also have property. We'll do properties in here like algebraic properties, like commutative property, things like that. So an example of deductive reasoning would be concluding that you will get a lunch detention for being late to class because that's what the rule says. The rule says if you're late to class, you're going to get a lunch detention. So you conclude, oh, I'm late to class, I'm going to get a lunch detention. Okay, so that's just an example. So if you're basing your reasoning on, or your conclusion on a definition, an assumption in society, a rule that's been stated somewhere, or some kind of property, then definitely that is deductive reasoning. Okay, so in geometry specifically, assumptions are called postulates and rules are called theorems. Okay, so let's give some examples of axiomatic systems outside of the realm of geometry. So I have the legal justice system. So I looked up something. Let's define armed robbery. Okay, so I read online that armed robbery is when you are robbing someone with a threat of force using either some kind of weapon or a convincing replica of a weapon. So robbery with bodily threat via a weapon or convincing replica. Okay. Now, the assumption that's a definition of what armed robbery is, but the assumption that we would make in our legal justice system is doing this is bad. We should not be robbing people. That is not good to do. So robbery is bad. We don't prove that. We don't define that. We just take it as an assumption and take it for granted that that is true. And then the rule could be something like the consequence of it, like if you commit armed robbery, I read online that you can get between 5 and 10 years in jail. You could be sentenced 5 to 10 years in jail. Not worth it. Okay. So that's an example within the axiomatic system. We talked about how many systems that you could enter in life would be an axiomatic system. The system of going to school. We have assumptions like you have to come to school. We have definitions like what is truancy? What is this? What is that? And then we have rules like, if you don't come to school, then X, Y, and Z will happen. Sports are very axiomatic. They have definitions, assumptions, and rules. We talked about softball and how the assumption is there's a ball involved. A definition would be like, what's a strike? What's an out? What's, these things. And then the rule would be like, if you get 3 strikes, then you're out, that kind of thing. So that's examples within that system. So this can be very valuable because whenever you go into a new system, be it when you're a teenager and you go to high school, or you go get a job, or you go to church, you enter a system in which you got to learn the lay of the land. You got to learn what the rules are and what the terminology is so that you can operate and function in that system effectively. So this is a valuable life skill here. All right. Conjecture. A conjecture is a conclusion based on evidence. It can be inductive or deductive reasoning. It's not like one of them is good and one of them is bad. You are more familiar with inductive reasoning and less familiar with defining deductive reasoning. And we're really going to be using that mostly deductive the rest of the year. So that's what we're trying to learn about it. But that's what a conjecture is. And a counterexample is an example that proves a conjecture false. Like when we were in class, I said, show me a counterexample to the statement that everyone in this room is wearing a red shirt. And just that day, I was not wearing a red shirt. So you could point to Mrs. Bayless and say she's not wearing a red shirt. So that's a counterexample. It's very easy to prove something false. All you have to do is find one counterexample. It's harder to prove that something is true. And that's why we're going to spend the whole unit talking about that. All right, so here's some examples of the types of problems you would have on assessments to show that you understand these concepts. Example 1, write a conjecture to describe the pattern and find the next 3 terms in the sequence. So for A, it's 1, 4, 9, 16. Okay, and when we went over this in class, we know that these are perfect square numbers. Okay, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So the next number would be 25, which is 5 squared, 36, which is 6 squared, and 49, which is 7 squared. You can also say there's a pattern of adding consecutive integers, like starting with 3, add 5, add 7, add 9, add 11, add 13. So that's also another way you could describe that pattern. The next one is more of a picture pattern. So we can see we have a dot, then we have 3 dots. So we added 2 dots underneath the 1, like here and here, like if I was to add one here and add one here. Then we added under these 3, we added 3 more. Each time we're adding 1 more set of dots. So the next picture, we'll add another row. And then we're going to do it again. I hope I have room to draw this. 1, 2, 3, 4. 1, 2, 3, 4, 5. That's the next term. And then 1 more. Now, this is one that I wouldn't expect you to describe the way I would because you're probably not familiar with the term, but you could say like you're making pyramids and adding another row of numbers each time that has 1 more dot than the previous. That kind of explanation would be 100% perfectly acceptable. We learn that these are called triangular numbers. So that's how I'm going to describe them, which is basically, the number starting with 1, and you can add consecutive integers of 2, then add 3, add 4, add 5, add 6, or you can say it's the number of dots that you can use to make a pyramid. All right. So the next kind of problem would be writing conjecture about a relationship. So you write down some statement that is true based on the information that you have. So there could be more than one possible answer. So the first one I said, angle 1 and angle 2 are a perpendicular pair. And this is what a perpendicular pair looks like. There are some true conjectures you could make on that. Measure of angle 1 plus measure of angle 2 equals 90. Another conjecture, you could say angle 1 and angle 2 are adjacent. That's true. You could say they're complementary. You could say their non-common sides form a right angle. This side down here and this side going up. So there's lots of true conjectures that you could say. Angle 1 complements. You don't have to write them all. Just a couple of possibilities there. All right, and the third and final example, tell if the conjecture is true or false. If it is false, you have to give a counterexample. All right, it says M is in the interior of angle AOC. AOC. So there we go. And M is somewhere in the interior, so I'm going to put it there and draw the ray. Does that mean that the measure of angle AOM plus MOC is going to add up to AOC? Absolutely, that's true. That's angle addition postulate. So we know that the two parts add up to the whole. Okay, next. If n is an integer, so integers are -3, -2, -1, 0, 1, 2, 3, and so on both ways. If n is an integer, the n squared is bigger than n. Well, that's true for most of the integers, like 2 squared is bigger than 2 because it's 4. 3 squared is 9, which is bigger than 3. But it's not true for these three integers, so they could all be a counterexample. -1 squared is not, well, that one is true. I'm sorry. -1 squared is 1, which is bigger than -1. So that one we're going to take out of there. So actually it only is false for these two. So they will be our counterexamples. Okay, counterexample is 0 because 0 squared equals 0. It's not greater than 0 like the problem said. And then 1 because 1 squared equals 1. It's not greater than 1 as the problem said. All right, so that is the end of this lesson on reasoning and conjecture. Join us for the next lesson. We will be talking about conditional statements.